Good morning. This is our 23rd lecture on statistical mechanics. And today we'll try to derive the expressions for thermodynamic properties of quantum ideal gas. First, we'll try to evaluate the pressure exerted by a quantum ideal gas. So, pressure exerted by a quantum ideal gas. For the purpose, we define a momentum distribution function Fp, which is Np divided by Hq. We consider a container filled with ideal quantum particles and the face ABCD is perpendicular to x-axis. So, if the particle is moving with velocity Vx along x-axis, the momentum transfer per collision will be 2m Vx, where we have considered perfect elastic collision between the particle and the wall of the container. So, this is momentum transfer per second, momentum transfer per collision per particle is 2m Vx. Now, number of particles incident per second on this wall which is perpendicular to x-axis, that is ABCD, will be those particles which are present within the volume Vx into unit area. So, if we want to find number of particles incident on unit area on the wall ABCD which is perpendicular to x-axis, it will be those particles which are present within a volume Vx multiplied by unit area. So, this volume is Vx. So, number of particles incident per second on unit area of the wall perpendicular to x-axis is that which is present in the volume Vx, and that number will be Fp d3p, that is elementary volume in momentum space, multiplied by Vx. So, momentum transfer per second per unit area on the wall ABCD, momentum transfer per second per unit area on the wall ABCD which is perpendicular to x-axis, that will be 2m Vx into Vx into Fp into d3p. Now, this Fp as we have defined will be 1 by h cube into 1 by z to the power minus 1 e to the power beta epsilon k minus or plus 1. If it is minus, that means it is for bosons, plus means it is for fermions. So, in one go, we will find pressure exerted by both the ideal Fermi gas and ideal Bose gas. So, to find the pressure P, we will write 2m Vx into Vx d3p 1 by h cube into 1 by z to the power minus 1 e to the power beta epsilon k minus plus or plus minus 1, doesn't make any difference. We just have to remember that plus is for Fermi gas and minus is for Bose gas. And we have to integrate it over the total volume in the momentum space for all Vx greater than equal to 0, means for positive Vx. So that we are taking into account the fact that the particles having velocity along positive x direction will be colliding against the wall ABCD. This we can write as integral minus infinity to plus infinity for Vx. Now this was for positive Vx, means 0 to infinity. We are taking minus infinity to plus infinity, so we must divide it by 2. So 1 by 2 and then 2m Vx square by h cube into d3p divided by z to the power minus 1 e to the power beta epsilon k plus minus 1. Epsilon k is energy corresponding to kth state. Random motion of the particles also suggests that v square by 3 will be Vx square, because v square will be Vx square plus Vy square plus Vz square, and Vx square is equal to Vy square, and that is equal to Vz square. You see, v square equal to Vx square plus Vy square plus Vz square, and for complete random motion Vx square is equal to Vy square, and that is equal to Vz square. Hence, for Vx square we can write v square by 3, and let's write this as twice of half m v square by 3 divided by h cube into, now d3p is 4 pi p square dp divided by z to the power minus 1 e to the power beta epsilon k plus minus 1, and this integral from minus infinity to plus infinity. We will change it to k space. From momentum space we change it to k space, and p is equal to h cross k that we have seen earlier. K is 2 pi by lambda. That means this p is equal to 2 by 3 h cube. Half mv square we can take as energy, so epsilon, because this is an ideal quantum gas, so energy is only kinetic energy, and 4 pi we take out. For p we write h cross square k square for p square, and for dp we write h cross dk divided by z to the power minus 1 e to the power beta epsilon k plus minus 1 integral minus infinity to plus infinity. I am sure you understand that this k is wave vector, and k here in epsilon k is representing the kth state. So this k is wave vector, that is 2 pi by lambda over here dk, but epsilon k is the energy of the kth state. We can write this as 2 by 3 h cube. Now 4 pi k square dk, that can be written as d3k, that is elementary volume in k space. Further, h cross square is, rather we have h cross cube, here also there is h cross. So h cross cube will give us h cube divided by 2 pi to the power 3. We have taken particles in the kth state. So this epsilon, the energy is basically epsilon k. So let's write epsilon k and divided by z to the power minus 1 e to the power beta epsilon k plus minus 1 and integral from minus infinity to plus infinity. This h cube gets cancelled, and then we have 2 by 3 2 pi whole cube into epsilon k d3k divided by z to the power minus 1 e to the power beta epsilon k plus minus 1 integrated from minus infinity to plus infinity. That is the expression for the pressure. So we get P as 2 by 3, 1 by 2 pi to the power 3, integral minus infinity to plus infinity, epsilon k d3k divided by z to the power minus 1 e to the power beta epsilon k plus minus 1. Let's write this as P equal to 2 by 3, 1 by 2 pi whole cube, and expand this d3k. So we get 4 pi k square dk epsilon k divided by z to the power minus 1 e to the power beta epsilon k plus minus 1 integral minus infinity to plus infinity. Now when we substitute beta epsilon k equal to x square, beta is 1 by kt, k Boltzmann constant here, then we get h cross square k square by 2m. This is k, capital KT, capital K I am writing for Boltzmann's constant, that is equal to x square. So we get for k, small k is for wave vector. So k is equal to x into 2m capital K T divided by h cross square under root. So we get for P 2 by 3, and in the denominator we have 8 pi cube. So we have 2 pi square minus infinity to plus infinity. Now epsilon k we are writing h cross square k square by 2m. So we will write here h cross square by 2m, and for k square we write from here. So 2m capital K T divided by h square into x square, and for k square we again write from here x square, that makes is x to the power 4 square of this quantity, and dk from here will be dx and under root 2m kt by h square. So that will make this 5 by 2. If you place it over here, this power will be 5 by 2. 5 by 2 divided by z to the power minus 1 e to the power x square plus minus 1. You can check yourself. You just have to substitute it over here. This is h cross square here. So that will be equal to 2 by 3. Let's take one kt, capital KT, divided by 2 pi square h cross square. 1 h cross square will be cancelled, so we will get h cross square to the power 3 by 2 in the denominator and 2m to the power 3 by 2 in the numerator, and kt to the power 3 by 2 in the numerator, because 1 kt we have taken outside. So that will be 2m capital KT divided by h cross square to the power 3 by 2 into integral minus infinity to plus infinity x to the power 4 dx divided by z to the power minus 1 e to the power x square plus minus 1. So we get this expression for P. Let's rewrite it. P by KT, K capital, Boltzmann constant. So P by KT can be written as, you see, 2 by 3 1 by 2 pi square into, let's take this as 2m kt, that is capital K, divided by, instead of h cross square, let's take h square, 3 by 2. That means we have in the numerator 2 pi to the power 3 x to the power 4 dx divided by z to the power minus 1 e to the power x square plus minus 1 integral minus infinity to plus infinity. That will give us P by capital KT is equal to, you see, from here this 2 gets cancelled with this 2 and 8 we have in the numerator. So 8 by 3, and we have now pi in the numerator. We have, let's take one root pi in the denominator. So we have now in the numerator pi to the power 3 by 2, which we take inside. So we write 2 pi m capital KT divided by h square to the power 3 by 2 integral minus infinity to plus infinity x4 dx divided by z to the power minus 1 e to the power x square plus minus 1. Now thermal wavelength lambda we have defined as h by 2 pi m kt under root. This whole thing is under root, means that will be h square then. So this quantity here is 1 by lambda cube. So we can write P by capital KT is equal to 8 by 3 under root pi 1 by lambda cube integral minus infinity to plus infinity x4 dx divided by z to the power minus 1 e to the power x square plus minus 1. So that is for P by KT. The evaluation of this integral we will do later on. Right now This is the expression for P by Kt in terms of lambda and this integral. This integral is very important. We will come across this integral a number of times as we advance in the course. So 8 by 3 root pi 1 by lambda cube integral minus infinity to plus infinity x to the power 4 dx divided by z to the power minus 1 e to the power x square plus minus 1. Energy we can write as summation over k nk epsilon k, where nk is number of particles in the kth state and epsilon k is the energy of the particle in the kth state. And that can be written as sum over k epsilon k divided by z to the power minus 1 e to the power beta epsilon k plus minus 1. You see, this k is for the state. It shows it is in the kth state. It is not wave vector. It is not Boltzmann constant. In thermodynamic limit, the energy is a continuous spectrum. So this summation sign will be replaced by integration sign, and we write this as epsilon k divided by z to the power minus 1 e to the power beta epsilon k plus minus 1 d3p d3q integral for the whole range. Now epsilon k is h cross square k square by 2m. K is wave number over here, and p is equal to h cross k, the wave number. d3p is 4 pi p square dp. So we write integral for epsilon k, it is h cross square k square by 2m. There is one h cube missing in the denominator. d3q will be integrated separately, and that will give the total volume V. So let's write V for that. Integrated value of d3q. We take this h cube over here. Now d3p is 4 pi p square dp. Now p is h cross k, so that is h cross square k, this is wave vector, h cross square k square, and dp is h cross dk divided by z to the power minus 1 e to the power beta epsilon k plus minus 1. We understand epsilon k will be written as h cross square k square by 2m. So we get this as V into 4 pi into h cross to the power 5 divided by 2m h cube k to the power 4 dk divided by z to the power minus 1 e to the power beta epsilon k plus minus 1 integral. Now, as usual, we substitute beta epsilon k is equal to x square. So we get from here k, that is wave vector, is equal to x into 2m capital K, that is Boltzmann constant, t divided by h cross square under root. So when we substitute here, this is V into 4 pi h cross to the power 5 divided by 2m h cube into, now for K4 dk we substitute from here. K4 means 2m capital K, that is Boltzmann constant, T divided by h cross square of this, but we will get 1 under root 2m kt by h cross square for dk also, so 5 by 2, and x4 dx divided by z to the power minus 1 e to the power x square plus minus 1 integral. Obviously, for x this integral will go from 0 to infinity. This is E. Let us rewrite this as V into 4 pi h cross to the power 5 divided by 2m h cube. Now this term let us write as 2m, this is capital K, that is Boltzmann constant, T divided by h cross square and multiplied by 2 pi m capital K T divided by h cross square to the power 3 by 2. We have an extra pi to the power 3 by 2 added over here. Otherwise, when you multiply these two terms, you will get this back. So we divide this by pi to the power 3 by 2 and integral x4 dx divided by z to the power minus 1 e to the power x square plus minus 1, 0 to infinity. Now when you simplify this 2m will be cancelled with this 2m. H cross square will give us h cross cube. So V into 4 pi. Now this h cube cancels with h cross cube, will be left with 2 pi cube in the denominator, and capital KT from here, and this quantity is 1 by lambda cube. Only thing is this h cross square. So let's write 2 pi m capital KT divided by h square to the power 3 by 2 means we will get 2 pi to the power 3 by 2 means cube, because this is h square, and we have 1 by pi to the power 3 by 2 integral x4 dx divided by z to the power minus 1 e to the power beta x square plus minus 1, only x square, this is e to the power x square plus minus 1, 0 to infinity. So now this 2 pi cube gets cancelled with this 2 pi cube, and we are left with V into 4 divided by root pi. This pi and this pi to the power 3 by 2, K capital T, Boltzmann constant, 1 by lambda cube, integral 0 to infinity x to the power 4 dx divided by z to the power minus 1 e to the power x square plus minus 1. This is E, that is equal to V into Boltzmann constant KT, and let's take here 3 by 2 outside, and then we are left with 8 by 3 under root pi 1 by lambda cube integral 0 to infinity x4 dx divided by z to the power minus 1 e to the power x square plus minus 1. Now if you remember, this quantity is P by kT. You see, from here we had shown this, that this quantity is P by kT, and we have exactly that quantity here. So this is P by kT, K Boltzmann's constant, T. So now we get for V, for E equal to V into, you see, this is kT will be cancelled, 3 by 2 P. So we get P equal to 2 by 3 E by V. So pressure is 2/3 of the energy density E by V. You see, we have not yet calculated this. We have not evaluated this integral. So that's why what we have done is, we have used conversions to get an expression for energy in terms of this quantity, which is equal to P by kT. And then we obtain the expression for E as 3 by 2 PV, or P is equal to 2 by 3 E by V. Remember that this holds good for ideal Fermi and Bose gas as well as for the classical gas. So it is true as long as one can say that particles move in 3 dimensions with energy momentum relation epsilon is proportional to px square plus py square plus pz square. Let us discuss the entropy of an ideal quantum gas, and we will try to find an expression for the same. We have shown earlier that S by K is equal to summation over I Gi beta epsilon I minus log Z divided by Z to the power minus 1 e to the power beta epsilon I minus 1 minus log of 1 minus Z e to the power minus beta epsilon I. This is for bosons, where this summation over I is running for both the terms. Similarly, this is the expression for S by K for fermions, and this is for Boltzmann gas. Let us start with the expression for Bose gas. So we have summation over I Gi beta epsilon I minus log Z divided by Z to the power minus 1 e to the power beta epsilon I minus 1 minus log 1 minus Z e to the power minus beta epsilon I. This summation over Z is for both the terms, and that is S by K. This is summation over the cells. Now when we switch from sum over cells to sum over states, we write summation over I Gi is replaced by summation over P is the state, into 1. So when we switch from summation over states to summation over cells to summation over states, we get S by K equal to sum over P beta epsilon P minus log Z divided by Z to the power minus 1 beta epsilon P minus 1 minus log 1 minus Z e to the power minus beta epsilon P. Summation over P is for both the terms. Now when we separate the terms, we write beta epsilon P divided by Z to the power minus 1 e to the power beta epsilon P minus 1 minus this log Z divided by Z to the power minus 1 e to the power beta epsilon P minus 1 minus of summation over P log of 1 minus Z e to the power minus beta epsilon P. Now we can take this log Z outside from here, and we get minus of log Z summation over P 1 by Z to the power minus 1 e to the power beta epsilon P minus 1, and that is going to be N, and this quantity, that will be the energy E. So we obtain S by K equal to minus N log Z plus beta E. E is the total energy, minus sum over P log 1 minus Z e to the power minus beta epsilon P. Let us now evaluate this summation. Summation over P log of 1 minus Z e to the power minus beta epsilon P. Now, in thermodynamic limit, this summation will be replaced by integration, and that will be integral C delta tau by h cube. Let us write d tau by h cube, d tau by h cube into log of 1 minus Z e to the power minus beta epsilon, where d tau is d3q d3p, and epsilon or epsilon p is equal to p square by 2m. So we get this equal to integral log of 1 minus Z e to the power minus beta p square by 2m d3p d3q. Now this d3q will be integrated separately, this divided by h cube we have. So this integration will give us the volume V. So we have V by h cube integral log of 1 minus Z e to the power minus beta p square by 2m d3p, that will be 4 pi p square dp. Now P is equal to h cross k, where k is wave vector. So we get V by h cube into integral of log of 1 minus Z e to the power minus, you see this is beta by 2m, and for P from here we write h cross square k square, and 4 pi we can take outside. For P square we write from here h cross square k square, and for dp we write h cross dk. So we get 4 pi V divided by h cube multiplied by h cross cube integral log of 1 minus Z e to the power minus beta h cross square k square divided by 2m k square dk. Now we are integrating over k. We will take it from 0 to infinity because wave vector will not be negative. We integrate it by parts, taking log as the first function and k square as the second function. So we have this equal to 4 pi V. Now this h cross cube by h cube, let's take as it is h cross cube, and when we integrate, first term will be k cube by 3 into log of 1 minus z e to the power minus beta h cross square by 2m into k square. Limit for this will be from 0 to infinity, minus integral of, we will write k cube by 3, and when we differentiate this, it will be 1 minus z e to the power minus beta epsilon, let's write for the sake of brevity, and in the numerator we will have z into e to the power minus beta epsilon into beta h cross square k divided by m. Minus will be cancelled, multiplied by dk, because one minus will come from this minus z and the other one from the power of exponential. Now when we put 0, k is 0, so this whole thing becomes 0, and for infinity this exponential term will be 0. So we get log 1 and log 1 is 0. So this term contributes 0. So that is equal to, this minus sign will be there, 4 pi v h cross cube divided by h cube multiplied by k cube by 3 into beta h cross square k by m and z e to the power minus beta epsilon divided by 1 minus z e to the power minus beta epsilon dk, an integral of this from 0 to infinity. This also is from 0 to infinity. So we get minus 4 pi v by h cube. Now we have h cross square here, so that makes h cross to the power 5 beta divided by 3m, and we have k4, k to the power 4 dk divided by, you see, when we divide both numerator and denominator by this quantity z into e to the power minus beta epsilon, we will get z to the power minus 1 e to the power beta epsilon minus 1 in the denominator, and that is integrated from 0 to infinity. Now let's substitute as usual x square for beta epsilon. So beta epsilon is h cross square k square divided by 2m kt, because beta is 1 by kt. So k comes as, k is wave number, x into 2m, this k is Boltzmann's constant, capital K, divided by h cross square under root. This wave number we are representing by small k, and the Boltzmann constant by capital K. So when we substitute this, we get minus 4 pi v h cross to the power 5 divided by h cube. This beta is 1 by kt, let's write beta only, divided by 3m, and for k to the power 4 we write 2m k this k is capital K, kt divided by h cross square whole square. And for dk, you see, this is x4, and for dk we again get this under root 2m kt by h cross square under root. So this will be 5 by 2, power will be 5 by 2 over here. x4 dx divided by z to the power minus 1 e to the power x square minus 1 integral 0 to infinity. If you remember, we have shown that P by Kt, K is Boltzmann's constant, is equal to 8 by 3 root pi 1 by lambda cube integral x4 dx divided by z to the power minus 1 e to the power x square minus 1, minus or plus both, from 0 to infinity. This we have shown earlier. So for this integral that we have, we can substitute from here in terms of P and Kt. So let's write for this integral, we will write minus 4 pi v h cross to the power 5 divided by h cube 1 by 3m, this is capital Kt, 2m capital Kt divided by h cross square to the power 5 by 2, and for this integral we get P by capital K T 3 root pi lambda cube divided by 8. This 3 gets cancelled and 4 we get 2 here. So we obtain minus v into, you see pi here and there is root pi, so that becomes pi to the power 3 by 2 h cross to the power 5 divided by h cube m capital Kt. Now this term we separate, we write 2m capital Kt divided by h cross square and 2m capital Kt divided by h cross square to the power 3 by 2 P by Kt capital K lambda cube divided by 2. This 2m gets cancelled with 2 and m over here. This Kt will be cancelled with this Kt. Now h cross square and h cross to the power 5 will make it h cross to the power 3, that is minus v. This pi to the power 3 by 2 we can take inside over here. So we will get h cross cube divided by h cube 2 pi m Kt divided by, let's take h square only, to the power 3 by 2. That means 2 pi to the power 3 by 2 will come out. P by Kt lambda cube. Now this is 1 by lambda cube, will be cancelled with this lambda cube, and when we cancel h cross cube with h cube, we will get 2 pi cube in the denominator, which will be cancelled with this 2 pi cube. So we are left with minus V P by capital K T. So we have obtained summation over P log of 1 minus Z e to the power minus beta epsilon P equal to minus PV by KT. So for this summation, we get minus PV by KT. So when we substitute it over here, we obtain S by K for a Bose gas. So when we substitute minus PV by KT for that summation, we get S by K is equal to minus n log Z plus E by KT plus PV by KT. Now Z is e to the power alpha and alpha is mu by KT, or e to the power alpha is e to the power mu by KT. So log Z will be mu by KT. So we obtain S by K when we substitute for log Z, mu by KT. So minus n mu by KT plus E by KT plus PV by KT. So K gets cancelled, and then finally we obtain S equal to 1 by T E minus mu n plus PV as the entropy of an ideal Bose gas. For ideal Bose gas, this is the entropy. Similarly, if somebody starts with the expression for Fermi gas, that is from this expression, this will also lead to the same equation. S in this case also will be equal to 1 by T E minus mu n plus PV. You can check it exactly in the same manner. When you proceed exactly in the same manner, you will find this expression. So this is true not only for ideal Bose gas, this is true for ideal Fermi gas also. One can check that we obtain 1 by T equal to dou S by dou E at constant P, V and N, which is a known fact for us. Let's find Helmholtz free energy. F is equal to E minus Ts, and from here E minus Ts will be mu n, and as it is for equilibrium system we can write mu n bar minus PV. From here we obtain Maxwell relations dou F by dou V at constant S will be equal to, at constant n bar will be equal to minus P, and dou F by dou n bar is equal to mu when P and V are constant. These relations are called Maxwell's relations. Now this relation for F, which is mu n bar minus PV, can also be written as n bar into, now mu we have seen e to the power mu by kt is equal to z. So mu will be kt log z. So we can write for mu kt log z minus PV. But we have also shown that summation over P log of 1 minus Z e to the power minus beta epsilon P is equal to minus PV by KT. So we can substitute for PV F equal to N bar KT log Z plus KT summation over P log of 1 minus Z e to the power minus beta epsilon P. So we can write F this way also. Of course, this will be for Bose gas, and for Fermi gas it will slightly change. F will be equal to N bar KT log Z minus KT summation over P log of 1 plus Z e to the power minus beta epsilon P. So that will be for Fermi gas. So we can write Helmholtz free energy in this way also. We will stop here for today. Next day we will see how to write equation of state of ideal quantum gases.